So far on this topic, we've done two examples of contingency tables where we had a two-way table, two variables, and we wanted to test to see if there was a relationship or not between those two variables. So the next thing for the chi-square test, we're going to be looking at something called the goodness of fit. Goodness of fit is testing and claiming about a proportion. Okay, we're going to be looking at, it's still considered a table. I would consider it a table. It's going to be a list of counts, and we're going to see, does that count, or does the count fit with what we think is supposed to happen? So proportionally, is the population fitting where it should be or not? Okay. A roulette wheel has 3 different colors on it, and each color has an equal chance of getting hit. Tested claim being 95% confident. So if you don't know the game of roulette, this is where in a casino you go up to the table and there's a big board with usually there's a 0 and then 1 to 36 on there. 0 is green, 1 to 36 is a mixture of black and red. You put money where you think a ball is going to land, where you spin it around a wheel, and wherever it lands, it hits. Okay. Obviously, there's one green spot, which is the 0, and there's a bunch of red and a bunch of black. So it should not be equal, but we're not going to go with this just because it's a nice short list to show you the steps of the calculation. The calculation of finding the test stat, finding the critical value, is very similar to the contingency table. Okay? So what we're looking at here, it's asking, or the claim is telling you, each color is hit equally. Here's our observed values. So again, obviously it's not. Red is 141, black is 150, green is 9. But let's just go with it to keep running this test. Okay? I'm not too worried about the conditions right now. There are some conditions that need to fit to be able to do this. I'm not too worried about that now. I just want to go through the steps to actually calculate the test statistic and find the critical value. Okay? So the first thing we need are null and alternative. This time, since we are looking at saying that these are equal chance of getting hit, we're not going to say the null. The distribution of colors is uniform. Uniform means equal. They're about the same. Red, black, and green are all getting hit about the same. Okay, again, equal, just like our null always is. Our null is always equal. The alternative, at least one is not equal to the rest. Now, again, using this data set, we can see which one is not equal to. We're not going to go into judging it right now. The alternative is just at least one is not equal. Next thing we have to do is find our critical value. So again, we need our degrees of freedom. You're using the same chart as before. We are 95% confident. So just as before, you're going to go across the 95%. Degrees of freedom is n minus 1. Now that n is the number of categories we have. So in this case here, 1, 2, 3 categories. 3 minus 1 is 2, so then you're going down to your chart to 2. Go over to the 95%, and that's going to be our critical value. We still have a curve that is skewed to the right. Our mark's going to be on the right-hand side tail, and I have 5.991. 5.991, and we still have the regular reject is in the tail, and then fail to reject. Now, I'm going to do 2 examples of goodness of fit, because what we have to do next is calculate our expected values, because the same work we did to find our test statistic for a contingency table is the same for goodness of fit. It's still the observed minus expected squared divided by expected. We already have the observed. That's what's given to us. We need to calculate the expected. So what we are going to think about here is, if this was true, if the claim was true, if all colors did show up equally, what would our expected values be? Okay? So what we have to do is add up our totals, add up our observational units so that we can split them up evenly. So if we're doing this, adding these up, 141, 159, that should add up to 300. And the key here for this one is the equal chance, saying that they're uniform. Because right now, to get my expected values, all I need to do is take that 300 and divide it by the number of categories. So for our expected, 300 divided by 3 is 100. So each one of our expected values is going to be 100. And now I'm just going to go ahead and do the same formula as I did for the contingency tables. I'm going to take each observed value minus the expected, square it, and then divide by the expected. So for each one of these, 141 minus 100 squared divided by 100. 150 minus 100 squared divided by 100. And then the last one is 9 minus 100 squared divided by 100. That's how I'm giving my three test statistics, 1, 2, and 3, and they should be 16.81, 25, and 82.81. And that should make sense. If those test statistics there are going down, okay, we can see 141 divided by 100, there's a pretty big difference there. 150 divided by 100, again, pretty big difference, and the test statistics pretty big. 9 compared to 100 is a huge difference. You get 82.81, so that's why when we add these up now, our test stat ends up being so large, 124.62. The larger the test statistic, the more likely we are to reject the null. In this case, if you're looking at our curve, same as before, reject, fail to reject, 5.991 is our critical value. Where does 124.62 land? All the way over there. It'd be way over in the reject area. So we're going to reject the null. Okay? We reject the null, and that means we're on a side and show that there's evidence for the alternative. At least one is not equal to, and we can see which one that is. Okay, that's obvious to see that the green is not equal or uniform with the red and the black colors. Okay? The next example that I'm going to show you in the next video is very similar to this, except it's not going to be a uniform test that we're running where we think each category is equal. Each category is going to follow its own proportion and have its own fit to the population.